velocity time graph for terminal velocity in liquid. The drag force in liquid, this is equal to FD equal to 6 pi eta RV. This is the Stokes law. Stokes law. Now eta is the coefficient of viscosity, where eta coefficient of viscosity, r radius of spherical body, v the velocity at time t. So I show you this by this. Suppose this is the body. This is a spherical body. This is falling vertically downward. Its weight is like this one, and here we will have the drag force. This is not drag force. The body is falling vertically downward. This is not V. So like this one we are having. So the net force will be how much? The force F equal to mg minus Fd. So this is equal to mg minus bv. This is equal to so much, where this b equal to 6 pi eta r. This so much. As we have taken this 6 pi eta r, this is equal to b. This velocity is ss. So this is now force. So now what will be the acceleration? Now F equal to ma equal to mg minus bv. So a equal to g minus bv upon m. This is the acceleration. So now we can have like this. This suppose we take the acceleration. Acceleration on this time, and we take the velocity on this axis, and this is the straight line equation. This is like this one, like this. At this point we are having this a equal to g. Here the velocity equal to 0, so this is a equal to g at this point. And when we are at this, here, now in this portion we have this a equal to g minus bv upon m. A equal to g minus bv upon m. And at this point, now we have this v equal to bt, the terminal velocity. This is the terminal velocity. So at this point the acceleration is 0. Acceleration is 0 here. So this A is equal to 0. A equal to 0. And this V is equal to Vt. So when we are having this A equal to 0, then we are having to this one. So now we can write to this. Now this acceleration dV upon dt equal to G minus bV upon m, or this dV upon G minus bV upon m equal to dt. Now then we integrate. Integrating with limits at t equal to 0, v equal to 0, and at time t, the velocity is equal to v. So now we integrate to this one, integration 0 to v dv upon g minus bv upon m is equal to integration 0 to t, and this is now u dt. Now this we have integrated. So now after integrating, now expression for velocity after integration now this is equal to v equal to vv upon m into e to the power minus bt upon m. This is not like this. This is mg upon v. mg upon v. This is now expression for velocity. So you can see from here that the velocity increases exponentially. It shows that the velocity of body falling vertically downward in liquid increases exponentially. Exponentially. So now BT graph is what? Now this is the graph that we take here. This is now velocity v, this is now time t, this is now 0. So what we have? The velocity is like this one. Like this. So now this is now point, suppose this is the point A, this is the point B, this is the point C, and B को थोड़ा सा और ऊपर ले लो इसको. Now this is C, and this is now point D. This is now point D. So now what we have? That from A to B, there is acceleration. Here, accelerated. Accelerated. Now, and in this portion, drag force has come into place. So this shows that the body is still acceleration. Is still accelerated. And in this portion, acceleration is 0. Acceleration. This is equal to 0. And this shows you the terminal velocity. Here, V equal to Vt, the terminal velocity. So in portion AB, from A to V, this is now Vt curve. For terminal velocity. This is not so much. Now then, from portion A to B, from A to B, the body is accelerated. The acceleration A is not equal to 0. And this B to C, from B to C, A is even not equal to 0, so it's still accelerated. Accelerated. So what we have in this position from B to C, now this force mg is more than Fd, the drag force. And now we can have that from C to D, C to D. What we have? The acceleration A is equal to 0. So this Bt equal to constant. So this V equal to Vt, the terminal velocity. Terminal velocity. So you can see from here that at the condition when if t equal to 0, then V equal to mg upon v, because as e to the power minus bt upon m, this tends to 0. So now this mg upon b. Now you can have that this is equal to, now v, that is equal to 6 pi eta. So now we have this, the terminal velocity bt. Therefore v equal to bt into 1 minus e to the power minus bt upon m. This is not so much. And at t tends to infinity, now this v is equal to vt as e to the power minus bt upon m. This tends to 0. No, this tends to 1. So this is equal to 0. So this v equal to mg upon v, this tends to 0. Now this v is equal to 0. V equal to 0. So now this at this t equal to infinity, then this factor tends to 0. This factor tends to 0. So here we get the terminal velocity of the body. So the body does not gain the terminal velocity immediately, but it takes a long time. This shows that body attains terminal velocity after a long time. After a long time. So now that the factor that we have this mg upon v, that is equal to the velocity, the time velocity, terminal velocity dt. So now we have this expression, as this t tends to infinity, then this expression, this tends to 0. So this v is equal to vt, and this shows that the body takes a long time to attain the terminal velocity. So this never happens that as the body is falling, then just it will gain the terminal velocity. No, it will take some time, because initially as the velocity increases, the drag force also increases, and then when this drag force equalizes the weight of the body, at that time the acceleration of the body is equal to 0. So the body attains the constant maximum velocity, that is called the terminal velocity. So this is about the velocity time graph for the terminal velocity in liquid. So thank you very much.